I ended the last video a little bit abruptly. I didn't even get to my other point, which is that there is a maximum flow rate of solvent that exists as well. So I'm not going to solve for it. I'm just going to show you that if you actually add so much water that you keep moving along this mixing line all the way until you reach the other side, you can't actually add too much solvent as well. Now, if you were to actually go through and figure out what this is, you may find it's going to be many multiples of the F, because you're going to have to add so much more solvent that it's going to have to be primarily solvent. Typically, that is not a question that you want to answer because you wouldn't want to add this much solvent anyway. Remember, you want to minimize cost as much as possible, and this wouldn't even be a design consideration anyways, unless you wanted to, for whatever reason, get down to super, super pure vinyl acetate in a single stage. But just keep that in mind, that there's a minimum solvent flow rate and paradoxically a maximum solvent flow rate that you can have in LLE. I want to get to the second part of the practice problem, which is that we want to add back the constraints that I've got 93% pure vinyl acetate again, and I want to do it in 2 equilibrium stages. So I want to constrain the flow rate to be the same for each stage. How much water should I add? This is a harder problem because this is an evaluate type problem. So the scenario here would be if I had, let's say, if I already had an existing 2-stage liquid-liquid extraction and I wanted to repurpose it for this, I'd have to evaluate if I could make it work. Or if, for whatever reason, my company only had enough money to purchase 2 equilibrium stages. If I was constrained in that, I would evaluate how I would make it work by adjusting the solvent flow rate. So go ahead and draw a process flow diagram. I'm going to do the same, but I'm going to pause the recording. Here is my process flow diagram. I've got 2 stages. I'm feeding an unknown amount of solvent, but I do know that solvent flow rate 2 is equal to solvent flow rate of 1, so I've at least constrained that. If I try and go through and work forwards like I have been, the first step is to find the mixing point of the first stage. So my overall balance looks like 500 plus S1 is equal to M1. So this is 2 unknowns with 1 equation, which isn't a problem. Well, it's a problem, but I need more equations to solve for it. So maybe I might want to do another material balance. This is typically what I do anyway. I need 2 material balances all the time. So 40 times 500 is 200. Doing an acetic acid balance plus 0 is equal to X M1 acetic acid. So that is an equation times M1. There's also 2 unknowns in this equation. So maybe I might try a third equation to see if I can get any closer. So vinyl acetate balance is 300 plus 0 is equal to X M1 vinyl acetate times M1. So this is 2 unknowns as well, and I mentioned that they're all different unknowns, so I can't solve a system of equations for them. So maybe you would be tempted at this point to try a water balance, and if you are really good at material balance, you know that what I'm doing now is a huge mistake and fool's errand. I just want to show you for sake of argument to not do this. My water balance says S1 is equal to X water 1 of the mixing point times M1, which also has 2 unknowns. And if I count the total number of unknowns, I have 1, 2, 3, 4, 5 total unknowns, 4 equations. And you might say, hey, wait a minute, I remember I have a physical constraint as well, and try to solve this problem. So you might say X M1 acetic acid plus X M1 vinyl acetate plus X M1 water is equal to 1. And now this equation has 3 unknowns, but if I look at the entire system, I have 5 equations, 5 unknowns, right? And this is wrong. Do not do this. What was the mistake that I made? I wrote 4 material balances, even though there's only 3 components. Remember, there's 4 material balances if I have the overall, but these are not independent equations. If I add the 3 component material balances, I will obtain the overall material balance. So doing this, you can waste a lot of time. If you were to say, I got 5 equations, 5 unknowns, and try and solve this system, you would run around in circles and you get down to the very end and you get something that's nonsensical. So you cannot go down this road. So this is not going to work. I'm just going to erase all this because we need a different approach here. So what are we going to do? So it's a guess and check problem. I have to make some initial guess in order to evaluate. And unfortunately, because I'm solving this graphically, I can't really goal seek in Excel. So the textbook, Lane, kind of goes through some ways that you can solve this in Excel. His way involves figuring out a fit for this data, fit for the equilibrium data. I think that's a little bit too much detail that I want to go into now, especially considering that we are online. So we're going to do just the graphical approach. Keep it within a margin of error. So it's not like you have to get the answer exactly correct if you're doing a guess and check type problem without the use of Excel. So how do I go about making an intelligent first guess? Remember in the last video, I talked about the minimum solvent flow rate. So I know that S min for the first stage is at least 117 moles per hour. So any guess that's less than that is automatically out. So I might bump it up a little bit. But then also remember, last lecture in part B, I asked the question that if you fed 200 moles per hour to each stage, how many stages would you need? And the answer to that problem was 3 stages. So if I think about, well, if I fed 200 moles per hour to each stage and it took me 3 stages, and now I have 2 stages, would I have to feed more or less solvent to each stage? So go ahead and pause the video, think about that for a second. And hopefully you would find that the stages is inversely correlated with the amount of solvent that I need. So if I decrease the number of stages, if I go from 3 to 2, I'm going to need to increase the amount of solvent. So S must be greater than 200 moles per minute. And that can help to inform my guess a little bit. So I'm going to make the initial guess that S is equal to 300 moles per hour and see what that gets me. So again, that's a guess and check type problem. I might find that with 300 moles per hour, I don't land directly on 93% vinyl acetate. Again, that is going to be okay, especially for liquid-liquid extraction type problems. So now that I have what my solvent flow rate is, so S1 is equal to S2, so on and so forth, I can then find mix point 1, 500 plus 300 is equal to 800. And in order to cut the video down so that you're not watching me just write equations out, I'm going to pause and work a little bit. And I encourage you all to do so as well. And I found my mixing point by saying that water, I added 300 moles. The mixing point was 800 moles. So 300 divided by 800 is 37.5. So I'm looking at my 37.5 water line and finding where it intersects my mixing line. That must be the mixing point. And then I've got a tie line that's pretty close, but I'll sketch in just another one, just so you get the idea of, well, it's really close. We're just going to probably use that tie line actually. All right, use the tie line to find the intersections of the equilibrium raffinate and extract composition. So I'll pause again and let you practice. Here are your compositions. I've drawn some red lines in for you to help you read where the points are if you're having trouble with that. These are what my compositions are. I'll pause again. The next step is to find the flow rate of R1 and E1. You may be asking yourself, well, if we know where the next raffinate phase is, why can't we just skip finding the flow rate, draw in our next mixing line, and then find the mix point there? You'd get stuck at this step because in order to find where along the mixing point this next mixing point lies, you have to know what the flow rates are. So go ahead and calculate those flow rates. Here's the work for that if you're interested. Again, 2 material balances, 2 equations. I find that my raffinate is 356 and my extract is 444. Coincidentally, one of my favorite Jay-Z albums too. The next step is to find where that second mixing point is, and if my next raffinate phase is close to 93%, we'll go ahead and call the problem solved. So I need to find mix point 2. Mix point 2 is 356 plus 300, so the solvent flow rates are still the same, 656, and let's do a water balance. Actually, you know what, I like pausing and making you do it as well, and then I think that'll cause for a shorter video. And I switched it up to do an acetic acid balance because it actually is a little bit simpler because there is no acetic acid in the solvent stream. So I find that my acetic acid at the mixing point is 10%, which is at that mixing point. I have another tie line that thankfully goes right through, so I can just trace my green line right on top. And then if I look at this point, this is my raffinate. I may be stretching it a little bit, calling this 93%, but again, there's error that is okay when you're doing these problems. So if I call this 93% vinyl acetate, I'm good, and I would call this problem solved with 300 moles per hour of water to each stage. Now, if I had to have great precision here, I would say that 300 is maybe not enough. So I'd have to go back to the very beginning, re-guess a new solvent flow rate, and then go through and solve the problem again. So you may say, well, if I don't want to go through the problem and have to solve it again, why wouldn't I guess something super high like 500 moles per hour or 600 moles per hour? Why wouldn't I overshoot it? And you could do that. That's not a bad way to go about the problem. But again, you're trying to minimize the amount of solvent that you want to feed to these stages. So you want to meet specifications. You don't want to exceed the specification too much. It's a frequent theme that reoccurs in separations. So that is all for lecture material today. Have a great weekend, and I'll see you on Monday.